Now what we're going to look at is a category of compounds called acids and bases. So before we can start trying to do chemical reactions with these, we need to talk about what they are. So first we're going to start with acids. My pen will work. There we go. So acids are going to be, now let's be clear, in case you've already learned some about acids or you start Googling them somewhere else, the definition I'm going to give is not the only definition used for acids. In the second semester of general chemistry, we're going to cover a number of different definitions for acids. So just know, if you already have some knowledge or you do some reading somewhere else and someone says something slightly different, that doesn't mean that they're wrong. It just means that they're using a different definition. So I just want to be upfront that this word can be more than one thing in different contexts. And we'll cover 3 different versions when we get to 1212. But for right now, what we're going to say is that acids are compounds that form H plus, my pit, there we go, when dissolved in water. Note, depending on what texts you're looking at or what materials you're looking at, this will sometimes be written as H3O plus and sometimes written as H plus. These terms both are meant to imply the same idea. There's technically some theoretical differences where you could argue which one's a better match for what an acid produces, or even maybe there's some other thing you should use, but they're trying to say the same thing as far as you're concerned from a general chemistry perspective. We put this thing in water, and we release some H pluses, either as H plus on its own, or that H plus is attached to a water molecule because the H plus doesn't stay on its own. So what does this look like? So for example, if I put HCl and I have it in water, what actually happens is it breaks apart into H plus and Cl minus. We don't have HCl connected together. Some people will instead write it the second way, and depending on the context, sometimes one is easier than the other. So you may see both in this class. This will write it as the HCl transfers an H plus to the water and forms H3O plus aqueous plus Cl minus. Both of these are ways of saying that HCl is an example of an acid. So this definition we're using is called the Arrhenius definition. So we're using the Arrhenius definition, which is that substances that produce H plus when they're put in water are acids. Note that the main way we're going to notice these compounds for the purposes of this class is going to be they're going to have an H somewhere on them that we can see comes off and then leaves an ion with it. Now, what we've looked at here, HCl, is an example of something we call a monoprotic acid. So what that means is that it only has one H that it's going to give up. And we call it monoprotic because it's an H by itself when it's an H plus. Hydrogen normally only has one electron. So if it loses that electron, it's just a proton. So we'll call it a monoprotic acid because it loses one H plus, and that H plus is effectively, it's just a proton. Most hydrogen doesn't have a neutron with it. Some isotopes of hydrogen do, but the majority of them don't have a neutron, so they're just a single proton floating around in water at that point, or attached to something else. Now, some acids are going to be what we call polyprotic acids. So that means these can release more than one hydrogen. So the most common example we'll use in this class will be H2SO4. This is an acid that can release 2 hydrogens. Sorry about that. So, now, we have acids, and you've probably heard the term before, so we also have bases. So what's going to be a base? So in this class, we're going to use the definition that bases are substances that produce hydroxide ions in aqueous solution. So for example, if you put NaOH in water, what actually happens is we have Na plus aqueous and OH minus aqueous. So this is an example of a base. So we have acids and we have bases. Now, the reason we're concerned about this is these things tend to react with each other, or they do. They undergo a reaction. The reason for this is by definition, all acids are going to release H pluses. All bases are going to release OH minuses. And if you have an H plus and you add an OH minus to it, well, that makes water. Water has 2 hydrogens and 1 oxygen and doesn't have a charge on it because the positive and negative, the hydrogen and the hydroxide cancel each other out. So if you mix an acid and a base, the way they react is they form a water, and then the rest of their ions will get together and do whatever they do. So what do I mean by that? Let's take a look at an example. Sodium hydroxide plus hydrochloric acid, the 2 we just looked at, when they react, these break apart. So I'm thinking of this like when we did precipitation reactions, where we broke them apart into their ions. This is Na plus and OH minus. This is H plus and Cl minus. We flip the anions. So now the OH minus is with the H plus. When it does that, it forms water. And then we have Na and Cl together, which, if we look up our solubility rules, that'll be aqueous. And then we can check that this equation is balanced. Everything balances out. We don't need to put any coefficients in front of it. That won't always be true. Sometimes you'll have to balance them by putting a 2 somewhere or a 3 or something. But this is the balanced chemical equation from the reaction of sodium hydroxide plus hydrochloric acid. So the pattern you have to have down to come up with balanced chemical equations is that if you have acid plus base, at least in the way we're defining acids and bases using the Arrhenius definition, it's going to react to form water plus a salt. And then you'll have to look up the solubility of that salt to see if it's something that's going to dissolve or not. Many times it will, sometimes it might not. So that's something you have to check. So this is the pattern. So if I tell you you're reacting an acid and a base, I don't have to give you the rest of the chemical equation. You can create that yourself. Now, you may ask, wait, how do I know if something's an acid or a base? So for the purpose of this class, there are a few acids and bases you have to know. In other cases, we're going to tell you if something's an acid or a base. Over time, you'll pick up some really common ones that are on this list you have to memorize. Plus, you'll learn more chemistry so we can start to learn how to define, oh, this is how I look at a molecule and figure out if it's an acid or base. And that will build over time as we learn more techniques for doing this. But for right now, we're just going to have a few you have to memorize. So first, we have the strong acids. So the strong acids are going to be HCl, which is hydrochloric acid. And I'd like you to know the names for these because they come up so often. Then we have HBr. This is hydrobromic acid. Man, it's going to be a long time to write all these acid names. Then we have HI, which is hydroiodic acid. Then we have HNO3. This is nitric acid. We then have HClO3, which is chloric acid. We then have HClO4, which is perchloric acid. And then finally we have H2SO4, which is sulfuric acid. So what does it mean when I say these are strong acids? A strong acid is one that completely dissociates in water. So what do I mean by completely dissociates? That means that if I take, let's say, HNO3 and I put it in water, 100%, or so close to 100% that it might as well be 100%, technically if you don't. But basically all of them turn into H plus and NO3 minus. Now, if it is not a strong acid and is instead of a weak acid, this isn't what happens. So if you have something like, let's say, acetic acid, it's the compounded vinegar. A small amount of the vinegar dissociates to form H plus, but a lot of it stays as the original molecule. So weak acids don't completely dissociate. So far in this class, we've always dealt with chemical reactions that go all one way. But as you go forward in chemistry, you're going to get more reactions where we deal with what happens when something doesn't completely react. What if some of the reactants stay and you only get some products? 1212 does multiple sections. The second semester of general chemistry does multiple chapters on how do we deal with reactions like this. So this class acts as that introduction. We're going to deal with some substances where only a little bit reacts. So, for example, if you have acetic acid, which is CH3COOH, it will have this little double arrow looking thing you may have seen sometimes in different resources you're looking at, or maybe from a high school class or just some other material you've seen. And what that means is that it doesn't completely break apart. Instead, we know that only a tiny bit of it turns into H+. Now, for this first semester class, we're just going to tell you only a little bit breaks apart. We're not going to define it numerically. What does a little bit mean? When you go on to the second semester of general chemistry, we will give you more math to work with to be able to define exactly how much we expect to break apart. So for right now, conceptually, it's okay just to know that weak acids don't completely break up. Strong acids do. So the final note I want to make is in addition to, I do want you to memorize these strong acids. This is relevant because it changes how we deal with some problems, whether they're strong or weak, so we'd really like you to know them. We also think it helps in the second semester of general chemistry, and they're compounds that get used commonly enough that we should be okay with it. The two other notes I want to make is I would like you to know that this is acetic acid. It's a weak acid. The reason I'd like to know that is we use it in a lot of reactions. It's relatively useful, and it looks different than a lot of your other acids that you're going to work with at first. You'll notice that the hydrogen that I say this lost actually occurred at the end of the molecule. Now, there's some reasons for that you'll learn in much more detail in organic chemistry, like where you put the hydrogens, how you know which one goes away. But I want to mention this one because it A, comes up so much, but B, it also doesn't look like a lot of your other acids. Many of the other acids we work with in general chemistry have a hydrogen up front, and that's the one that comes off. That's not the only way they work. There are plenty of acids in the world that have them at the end like this does instead. But for right now, I just want you to recognize that so you can see in a problem, know, oh, he's talking about an acid, rather than not realizing that's what it is and thinking it's something else. The other note I want to make here before I go to bases is that depending on the source you look at, some people might not say that chloric acid is a strong acid here. This one, I got to fix this pen so it quits doing that. I've got a little pen I use to write on my thing, and there's a little button on it that changes slides, and it's really sensitive, and it's where I usually hold it. So I try not to hit it, but as you can tell, I've done it 3 times already, and I'm sorry because I'm sure that's annoying. Okay, that aside, chloric acid is a borderline case. So it's true in all of these cases when we say they're strong acids and they completely break apart. Technically, not every single molecule not every single formula unit does. There will be a few that stay together, but they'll be on the order of something like 1 stays together, a trillion break apart, or a quadrillion, or some number like 10 to the 20th break apart, or something like that. You'll have really, really large numbers, and depending on which of the strong acids you're working with, that number is different. Chloric acid, though, is close enough to a borderline that some people would say, no, that's really not a strong acid, so you won't always see it in all the lists. I don't remember if the text I'm currently using does that or not, but it's close to the borderline. I think it makes a lot more sense when you get to the second semester and we start defining the weak acids and we start to sort them out too. Because even if an acid is weak and only breaks apart a little bit, some break apart way more often. Like you can find acids that break apart 10,000 times more often than acetic acid, for example, but they're still weak. So because of that, then we start to deal with that, and I think it makes more sense at that point. But right now, because we have an incomplete picture, we just have to say, look, these are the strong acids, they completely break apart. And for the practical purposes in almost every question you'll deal with, that's a really good assumption. And it's true also by my perspective for chloric acid as well. That's why I have it on the list of 7. Some people have a list of 6. Just know that that's where these definitions come from, so that can have a limitation of what someone would define. Now, the second set, we did our strong acids, so what about bases? So rather than trying to memorize specific compounds, I like to use the version where we use the solubility rules to do this. So our rule for strong bases, so these are bases that completely break apart, is that all soluble hydroxides, so remember that's the OH minus group, don't forget, with group 1 or 2 metals are strong bases. So, for example, we know that sodium hydroxide is soluble, and sodium is a group 1 metal, so that makes it a strong base. Whereas if we were to take beryllium hydroxide doesn't dissolve, so it can't be a strong base. So in this case, the idea is if it doesn't break apart in water, then it's not going to make a base because the hydroxides don't get released. They stay with the beryllium and they just stay as a solid. So it doesn't function like a base. So all of our strong bases are going to be the soluble hydroxides with group 1 or group 2. And over time, you'll start to recognize the ones you use a whole lot. And that's another good reason to know our solubility rules, to get comfortable with working with them, because we can use those to determine is something a strong base or not. Also, I'll be straightforward. You tend to use a couple really commonly, sodium hydroxide being by far the most common strong base that we use. The second thing to point out is that you have more strong bases that have more than one hydroxide, and that can be relevant for how you end up balancing a chemical equation. So, for example, let me make sure of something real quick, because I use an example in a problem in a bit. Yeah. So, for example, calcium hydroxide is a weakly soluble base. So, calcium hydroxide, you can't dissolve a whole lot, so you can't make it a super strong molarity. You can't make it a high molarity because the calcium hydroxide will stop dissolving, but a little bit will dissolve, and anything that will dissolve does break apart. So this one ends up being a strong base, but what's important is when it does that, this has 2 hydroxides. So the only acid we have to worry about that with is sulfuric acid of the strongs, but calcium hydroxide has 2 base elements, and then there's a few others that do too. So that can come up a little more often, and that comes up with your balancing chemical equations. It's either going to be it's going to be something like a polyprotic acid, or it's going to be a base with multiple hydroxides that cause your balancing not to just be write a bunch of ones, but instead to have to actually do some balancing when you get done. So make sure to pay attention to that when you're looking through this. The final note is actually something I meant to mention when I talked about acid-base reactions, so I'm just going to add this at the end because it's a term I forgot to use, that I think you've probably heard of before, and also I feel it makes sense when you hear it, but just to know it's what it's for, is we use the term neutralization reaction to talk about acid-base reactions. So if you have an acid and you add enough base to completely neutralize it, or to get rid of it, we call that neutralization, because we're getting rid of the acid components as we add a base, or we're getting rid of the base components as we add an acid. So to be completely neutralized, we need enough moles of acid and base to exactly react with each other. So if you have more moles of one or the other, based on the balanced chemical equation, react with each other, then you're going to still have a solution that's either acidic or basic. Now note, it means enough moles to react, so you have to have the balanced chemical equation. So for example, if you were using calcium hydroxide here, well, every calcium hydroxide can neutralize 2 hydrochloric acids, because each hydroxide reacts with one H+. An HCl only makes one H+, but this calcium hydroxide has 2 hydroxides. So each hydroxide can react with one acid. So you have to pay attention to the balanced chemical equation. And for it to be a neutral substance, you're going to have just enough acid to neutralize the base. If you have more of one than the other, then the solution will be acidic or basic in nature. Now, we're not going to go into detail about how we define acidic or basic solutions, but I will mention you have probably heard the term pH before, even if it wasn't inside a science classroom. So low pHs are solutions that are acidic. High pH solutions are ones that are basic. So this is our measurement tool, and we will use that significantly in the second semester. And I like to bring it up here just to mention that it's not that we've forgotten that. It's just we tend to talk about it in another class more, because we do a lot more numeric calculations when we get there with some of the tools we're working with. So we'll do that a lot more in the second semester. So right now we just have to know, is it acidic or basic, because are there more moles of acid or more moles of base? So which one's left over at the end based on the balanced chemical equation. So with that, we're going to... actually, I want to do one more thing. I know it's awful with at least I'm a video, so you know I'm going to keep going. It's not like in class when someone does that and you're like, oh, he's going to let us out. Oh, he had another idea. So you can see down at the bar, I got a couple more minutes. So I just want you to try one of these. So let's say you had hydrochloric acid and you added barium hydroxide to it. I want you to pause my video and come up with a balanced chemical equation for this. And then I'll go over it with you. So hopefully you did that. And if not, shame on you. Or you're really stuck, and that's okay. You can watch me. But remember that watching me do it is definitely not the same as doing it yourself. It's a lot easier once I've shown you how to do it. It feels really good to be like, oh, I watched Dr. Leslie. That makes so much sense now. I saw him do it. But you need to make sure you're practicing it on your own. If you couldn't do this one, that's okay. Watch me. But then make sure you go and practice somewhere else. Do the problems on my exam review sheet, for example. If you're not in my class and you found this video somewhere else, do practice in whatever text you're working with. Try some of these where you don't know the answer up front. Because until you can do it without already knowing the answer, you're not really quite there yet. And that's dangerous to think that I'm getting it, but then not. That's almost worse than not knowing it, right? Because then your brain tells you, I don't need to work on this anymore. Because as I explain it, it creates a lot of cognitive ease. It feels easy because I'm filling in all the blanks. And you may not recognize which blank it is you didn't know until you try a problem on your own and you get stuck in the middle and go, oh, wait, that's where I get stuck. This is where I need help. Because when I'm talking, I fill in all those blanks. And then your brain goes, okay, I got all this. We're moving on. We know acids and bases. Great. So just make sure to do some of these on your own as well, especially if you didn't get the right answer. Now, if you could do this one and you got it perfectly and you feel comfortable with acids and bases, that's okay. So after that short aside, let's do this. So we need to switch our anions. And instead of writing HOH, I'm just going to write H2O. And then we have BaCl2. And if I know my solubility rules, I know this is aqueous. You can look those up. Now, this reaction isn't balanced yet. So if you need to, you can write out all the numbers and track them. This is a simple enough one that I'm okay with doing it in my head by looking at a few things. So the first place I look at is, this chlorine. There's 2 on the right, but 1 on the left. I'm going to need at least 2 hydrochloric acids to balance that out. Well, I know I'm now having 2 acid molecules. This means I have 2 hydrogens, but my barium hydroxide also has 2 OH minus polyatomic ions. So if I'm combining those, that means I've got more hydrogens and oxygens than I have water. But if I double this, then I'll have 4 hydrogens and 2 oxygens on both sides. Specifically, I balanced the oxygens here was the easiest because hydrogen occurred in more molecules. So I have 2 oxygens on the left, 2 on the right now. I have 4 hydrogens on the right, 4 on the left, Yes, 4 on the left, 4 on the right. My brain was missing them for a second. And then I have 1 barium on both sides and 2 chlorine on both sides. So that's my balanced chemical equation. So that is the acid-base reaction between hydrochloric acid and barium hydroxide. So now I really will stop it because this has been long enough already.